assume all of you have opened up. Is it possible to minimize this crap? Hide chat. Okay, you will go somewhere here, and you will go. Fine. We'll just stick to it. So I'm starting with a fresh new file, and I'm starting with Grasshopper being opened up. And just a little bit, I already kind of talked to you about the form finding in Grasshopper. That's mostly what it's used for when you need to simulate things. And also there's Grasshopper is used for another thing, that is managing complexity. Let's say when you have 50 or 500 or 50,000, doesn't matter, different windows, and you want to add frames to all of them, then usually you use Grasshopper. You don't kind of go through those 50 windows and kind of create frames for each of them individually. So that is managing complexity. That's another part where Grasshopper is super useful for us as architects. But in this case, I'm going to just, I guess I'm just going to show you the basics. Let's begin with the facade part, right? I want to show you the facade. So as I mentioned before, in AADA 20 course, we had this kind of a Rhino Revit facade system that we created in Rhino with use of Grasshopper, where we use different types of tiles, right? And we kind of took those tiles and we populated them on some sort of a surface, right? That became our, come on, there we go, on some sort of a surface that became our facade, and those tiles were populated on it, right? Those tiles were not SubD geometry, and in this case, I'm going to show you a tutorial on how to do it with SubD. So the first thing is I'm going to make a surface that's going to be my facade, right? I think let's do something quite simple at first. So I will just kind of create a line segment. I'll start it from 0. Orthographic snapping, I'll turn it on, and I'll just do a facade that's, I'm drawing in millimeters, so it's going to be a pretty big one. A facade that's like 20 meters long, so 20,000 millimeters. Right? I'm just doing like a straight facade for now. I'll just kind of make a copy of, maybe let's do it this way. I'll make a copy of the line upwards, and let's say it's 5,000 millimeters, 5 meters high. And just create a loft on it. Yay, we managed to create a rectangular surface. Fun. So we have our surface, and I will, back in 0, 0, 0 coordinates, I'll create some sort of a element that is going to be populated on the surface, right? Let me move it a little bit back. And here I'll just use this place to create an element, right? So first of all, first things first, the size of the element for this particular example will not matter. My connection is unstable. Well, it seems to be back on track. The size of the element will not matter, right? So with SubD tools, I can create any kind of element, any size I want. So what I'm going to strive for is going to be Schwarz P. That's, I just killed that name. Surface. We will be doing something like this, or rather, I want to do something like this as my initial element for the facade, and it's going to be the Schwarz P surface. So this is called the Schwarz P surface, and it's basically a minimal surface, and it's also a triply periodic minimal surface, and there's a bunch of them. If you kind of just Google for triply periodic minimal surfaces, you'll be able to find quite a few. Is there like a blah 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 blah? I'm trying to find the. Yeah, there we go. So there's the whole list of them. And don't ask me why did they use the Comic Sans MS font. I don't know, but it's basically all of these surfaces have, according to their boundary, they have the minimum amount of surface area. That's why they are called minimum surface. And triply periodic means that they can be stacked in a three-dimensional array, and they will join up to their neighbors perfectly, right? That is so that makes them triply periodic minimal surfaces. And there's again a bunch of them, and we will be using, I can't find it now, it's somewhere here. Come on. Yeah, good enough. We'll be using this one, Schwarz-P surface. So let's build it up. Let's build it up in Rhino. And actually the one that I'm going to be kind of creating here is not going to be a perfectly minimal surface, because I will not be using any simulation on it to create, to make it minimal. It is going to be what I would like to call close enough, right? And that is good enough for us. So I'll begin by just creating a box, SubD box, and I'll make sure that X count, Y count, and Z count, all three of these are set to be 1, meaning that there's no subdivisions for the box. And I'll start from 0, so I'll just type in 0. And here I'll just type in the dimension. So I definitely want the box to be a cube, right? It needs to be like all of the 3 dimensions need to be the same. So I'll just type in 10, enter, 10, enter, 10, enter. Or you can just write 10, 10, 10. Or sorry, 10, enter, enter, enter. So you end up with a cube that is 10 by 10 by 10. Something like this, right? And I will just take the top with Control-Shift-Click. I will select the top of the cube, and I'll select the bottom of the cube, Control-Shift-Click, and I'll just hit delete to get rid of them. So now I have only the sides. Okay, and you can see that it with tab it smooths out to what's a circle basically. Okay. By the way, if you'll have any questions, just ask immediately. Don't wait for me to stop talking. So we have our cube now. I will make a copy of it, just up, doesn't matter where, above, and I'll rotate it 90 degrees, right? Something like this. And I'll just select it, hit M, short for move, enter, and I'll move it from, let's say, this corner point to this corner point to create this kind of a L shape, right? Or upside down L shape. If I hit tab, you can see that it's basically 2 cylinders. Okay, so we have this done, and now I can just kind of make a copy of that cube, rotate it along the z-axis, around the z-axis in 90 degrees, and also move it like so. So now we have 3 of them, right? Since I'm kind of lazy, I'll just take these 2 cubes and I'll just mirror them, use mirror, and I'll mirror them to the other side by just clicking on these 2 opposing corner points, here and here. Click, click, because this is like the mirror axis, right? For like copying or mirroring the 2 cubes to the other side. So now we have, well, now we're almost done, right? You can start seeing where I'm going with this, kind of looking at the Schwarz surface here, or maybe this is better, like looking at the Schwarz surface here and looking at the cylinders here or the cubes here. You can start kind of getting what I'm trying to do. So I'll take the bottom box and I'll just move it up, or copy it up to finish up this cross, right? So this is what we have so far. Once I select all of these and I type in join, hit enter, and hit enter again, everything will be joined up into one shape. And when I hit tab, those places where it joined up will be smoothed out. And thus we get the Schwarz-P surface, which is not exactly a Schwarz-P surface, I know, but it is close enough, right? It's good enough for what we're trying to do. Any questions so far? Okay, let's continue then. So this little guy right here is way too small for our facade. As I said, the scale of it doesn't really matter, but just kind of for selection purposes and for finding where the hell my brick is, it's way too small, right? So I'm going to kind of select it, and I will just I can just kind of type in scale, I guess. Scale around the 0 point, and I'll just scale it up 100 times, right? So that it's a big boy, right? Now I want this to be placed on this, and basically to be copied, right? Because I really want to, well, wait, let's see. So if this is 10 and this is 10 and this is 10, the length of my element is 30, right? So I can kind of select this element. I can click on any arrow, holding down the Alt key, and I can type in 30. But I kind of scaled it up by 100, so I need, it's going to be 3000 rather than 30, right? So 3000, 3000, and I end up with a chain like this. I can select these three, move them up in Z direction, 3000, and I end up getting something like this. I can join these up into one shape. I can hit tab, and I end up getting, you know, a structure that looks like this, right? So that is, you know, that the idea. But I want this to be automated, and I want it to follow the surface. That is the tricky part. Okay, so the first thing that we do between Rhino and Grasshopper to start working in Grasshopper is we reference in our geometry, right? We kind of create links from stuff that we have in Rhino to stuff that we will be working on in Grasshopper. So I'm going to create an empty component that is, let's use this. Don't worry about this part. This is just for annotation purposes. You'll see what it does in just a second. Let's do that, and let's draw full names. Yeah, that works. Okay, so I will be referencing in these two. One is going to be a surface, right? So I reference it as a SRF, as a surface. Remember, those black hexagon icons, they show nodes that are completely empty, right? And that don't do anything. They just hold geometry, and that's perfect for us. We want this particular node, surface node, to just hold this geometry, right? So I'll right click on the surface node. I'll choose set one surface, and I'll click on the surface here. Bam, that's done, right? So now these are linked. If I move this one, you know, the one that in Grasshopper will follow along. Great. That means we can mess around with it. So I'm going to hide it now in Rhino. I'll just keep the one that's in Grasshopper. In Rhino, I don't want to accidentally kind of select it, so it's hidden. And we will do kind of the same thing with this SubD geometry, right? So I need to link in the SubD geometry. I can do that by creating SubD node. You know, again, that black hexagon. I can do that with SubD node. Right clicking on it and choosing set1 SubD and choosing my SubD here. By the way, notice how even if in Rhino I have it set to show up as a flat, low resolution display or a flat display, in Grasshopper it's always going to show you SubD as a smoothed version. It doesn't recognize the low resolution version, right? I just hid it, by the way, in Rhino. So in Grasshopper, SubDs will always be shown smooth. That's just something to be mindful of. Okay, we have the SubD, we have the surface. We want SubD to follow the surface. How do we do that? Many ways. The answer is many, many different ways. One way that I already showed you how to do it in the Rhino Revit course was by the use of box morph command. This thing right here. Morph an object into a twisted box. So we use that box morph, and it has 3 inputs. And why does it not show me full names? I want full names. There we go, full names. So it has 3 inputs. Geometry, so that's going to be our brick, right? That's easy. SubD geometry goes in here, like that. Reference box, so we need some sort of a box for this brick. We need some sort of a box that represents the boundary conditions of this brick, and then target box, so it's going to stretch out that brick onto some sort of a target box. And I think I should explain this better. So let me do one thing. I'll just draw it as a diagram for you in 2D. So imagine you have some sort of a happy face on it. Something like that, and you have like 2 eyes, and you have a smile. A very happy face, right? Oops. Something like that. Yay, happy, right? And that happy face has some sort of a bounding box. It is placed and it can be placed in some sort of a in this case a rectangle, right? So if I write bounding box on it, I can see, this is basically the frame, the smallest frame for this happy face. And then I can if I have another box that is, let's say, twisted, right? One part of it is kind of extended. I can translate this happy face from one box to another, and also it will twist to fit inside of that other box, right? So this guy can kind of come in and goes here and kind of starts twisting. So I'm not going to be very kind of precise about it, but it's going to be something similar to that, right? So it's basically how it works in 2D. You have 4 corner points in well, not just 4 corner points. Every control point here has XY values, and it's going to be moved to the new XY values here. But basically, all it does is just twists the geometry to fit the new rectangle. In our case, it's going to be our star shape, our Schwarz-P surface. That's going to be the happy face. That's going to be twisted from some sort of a bounding box, right? So we need to create that bounding box. I'm going to say, like, make a little bit of room between these two, and I'll create a component that's called bounding box. Right here, bounding box component. And basically, what it asks us, what it asks of us is to give it some sort of content, some sort of geometry for it to create a box around, right? So I can just kind of connect my SubD to its content input, and it's going to generate, that kind of fitting box around it. And you can see that there are two outputs here. Don't worry about it. I'm not gonna go too deep into this. Just use the first one. Both of them in this case are going to be identical. In most cases that you will use, both of them are going to be identical. So just use whichever you want. I'll use the first one, and I'll connect it to the reference box, right? Reference input right here, right? So now we have our happy face. We have a rectangle that's surrounding our happy face, and now we need a twisted rectangle, right, on which we kind of will map this. We don't have that one, right? We need to create it. Let me move this up a little bit so that it's not in the way. And this is where we actually create those kind of boxes on our surface, right? Those twisted boxes on our surface for this element right here to be placed in. The way we do this is quite simple, but also it will require us to figure out a little bit of math, which is, always annoying to do, but it is what it is. So the first thing that we want to do is we want to tell the Grasshopper, yo, can you create a grid of boxes? A grid of boxes that would follow along the surface, right? Just X amount of boxes in one direction and Y amount of boxes in another, right? Can you do that? The tool that does that is called Surface Box, I believe. Surface Box? Yes, it is. It's called Surface Box. And if you kind of hover your mouse over it, it explains you what it does, right? Create a twisted box on a surface patch. So it creates a twisted box, a box that tries to follow the surface on a surface patch. That patch part is important, and I'll explain why in just a second. But basically, here we used surface box. Asks us of three things. Very easy to give it two of them, very hard, or not very hard, but harder to give it the third. Giving it a surface is easy because we have one, right here. Giving it a domain is going to be harder, and I'll explain what a domain is in just a second. And giving it height is also easy. Height is basically, for this wall, what's going to be the thickness of these boxes that are going to be created, right? So I'm just going to, we're working in millimeters. I'm just going to say 200 millimeters for each box, right? Just double click, type in 200, you'll get a slider, 200 millimeters. It's still not working. As you can see, it's orange because it doesn't have a domain. And this is where things get tricky. So a domain is, let me explain what a domain is real quick. A domain is written this way, 0 to 5, right? So it's a domain is basically a range of numbers. Domain is a range of numbers that go between 0 and 5, right? So this whole range is a domain, right? Simple enough. Why the hell the surface want a domain? That's the not so simple part, right? So think of it this way. We need to divide the surface into parts so that we know, how many boxes are we going to be creating in one direction and the other. And it asks us for domains. So the way it's going to work, it's not going to have a very simple domain. It's actually going to have like a double domain, 0 to 5, and then you do comma 0 to 5. I believe it's, or 0 to 8. Doesn't matter. I believe that's how it's written. It might be a little bit different. So basically, it's like a double domain. Why do you need a double domain? Okay, so here in the top view, or not the top view, but from the top view, let's say we have a surface, right? And that surface has 4 corner points. 1, 2, 3, 4. And each of those corner points have these kind of local coordinates, right? So this local coordinate is 0, comma, 0, right? X and Y, right? So 0, 0. Let's say this corner is 0, 0. Then this coordinate would be 1, comma, 0, right? So in X direction, it goes by 1, and in Y direction, it doesn't go by 1, right? It kind of doesn't move, so it stays at 0. So with that same logic, here it's 1, comma 1, and here it's 0, comma 1. By the way, notice how I'm using 1 as my maximum. That is because it's localized, right? So it's all proportion based, meaning that the center point right here is going to be 0.5, comma 5, comma 0, comma 5. I really suck at drawing with my mouse, but you get what I mean, right? So that's the middle point. So now how the hell do we say, give me this part of the surface, right? I want to just work with this part of the surface. We start working with domains, and we specify first a domain in, I believe it's first in this direction and then in this direction, right? So here we have a domain between, like, the overall length is between 0 and 1, right? So if I were to expand this, come on. I kind of looked at these lines separately, the horizontal and the vertical one. Come on, dogs. It would be basically 0 is here, 1 is here, and I need a point, or rather I need a range somewhere between 0, 1, and it would be 0.4, I think, or maybe 0.3. You know, I need this, and here I just specify I'm interested only in this range, right? Or in this range. You know, I'm talking about the same thing here. So I write it down as 0 to 0.4, right? In X direction. In this case, it's U direction, but whatever, right? And I repeat the same procedure for the Y direction, right? Or the V direction, which is going to be also 0, come on, 0, also 0, also 1, and let's say that's 0.2, 0, comma 2. Let's say here is 0, comma 2, here is 0, comma 4, and here I also write 0 to 0, comma 2, right? So I've just specified a range for another direction, which means that once I add these two guys up and I say that one represents the x-axis, the other one represents the y-axis, I get this area right here, right? And I know that I'm talking about this area. So with this, like with these two instructions, I can get any kind of rectangular patch, right, from anywhere on the surface. Or I can get series of patches, because I would just need another set of instructions for another patch, another set of instructions for another patch, and so on, right? So this is how it works. And I need to make sure that I will never ever use the scribble tool in Grasshopper, and anymore, because goddamn, that was painful. So back to domain. It asks us for a kind of a domain of the surface, and if I kind of give it 0 to 1, I can show you. I can write it 0 to 1. I believe it's going to be comma 0 to 1. If I write it like that and I give it a domain, it's freaking out. Okay, it needs to be different. Just give me a second. I need to remember how a squared domain is written. Oh, okay, so it's a little bit more difficult. U. So I can write it U that don't need a comma, V 0 to 1. So now I'm basically saying, you know, with this U from 0 to 1 and V from 0 to, why are you not working? Wait, I'm gonna force it to work, I promise. Oh, sorry, wrong brackets. So it has the curly brackets, not the smooth ones, not the regular ones. So it should work with the curly brackets. It doesn't. What am I missing? I'm gonna freak out now. Or is there something here? Is there something here? Sorry, technical difficulty. Okay, fine. We will use it this way. It doesn't like me writing it manually. It wants to get it from, yeah, it does want to get it from directly from a node. But basically this node, what it does, it creates like 0 to 1, 0 to 1 domain automatically, right? And here I can just kind of create any kind of domain as I want. And basically the output of it is this little box right here, right? So the question is, why is this box not following the whole surface, but rather it's this almost like a stick, right? A stick box right here. And the reason for that is because surfaces can either use local coordinates, you know, proportion based like this, you know, 0, 0 is here, 1, 1 is here, or surfaces can use dimension based coordinates, such as if 0, 0 is here and what was it? 20,000 comma 5,000 millimeters was here, right? And you can never tell in an instance which one is the surface using, but once I connected this domain to it, I can immediately see, you know, oh yeah, that's not good, right? That's not how it should work. Thankfully, you know, because it's like a 1 millimeter box. Thankfully, a solution for it is very, very simple, right? To force it to work with proportion, all you need to do is right click on the surface, like surface component or surface input here, doesn't matter. And you choose reparametrize, this one right here. So that reparametrize tool, what it does, it forces the geometry to be, like the values for the geometry to become proportional in proportion from 0 to 1 rather than dimensional in millimeters, right? So it becomes proportion based. Okay, enough blabbing, let's do it. I will delete the domain part, and here we have a surface and it's still waiting for a domain, and we need to give it like a grid of domains, right? So it needs to be multiple domains. Thankfully, there is a tool that does that, and that tool is called divide domain squared. You can find it, let's not type it in, but rather let's find it. It's under maths tab right here. Yeah, come on. Let me move it here like that. Yeah, there we go. So it's under maths, under domain, divide domain squared. The squared one is important because squared means that it's going to kind of calculate it along the x-axis and also along the y-axis of the surface, or u and v axes, if I need to be precise. So divide domain squared. It will ask us for three things, and it will spew out or give us segments. First thing that it asks us of is the domain, the base domain. And this is counterintuitive, but for the base domain, we will be using a surface. We will be using exactly this surface input. Because think of it this way, divide domain squared, it needs to know what it's dividing, right? It kind of needs to know what's the length, what's the height, to understand what is going to be dividing. That's basically it, right? Surface goes into domain here. U count and V count is basically how many segments we will have in both directions. So by default, it's set to 10, by the way. So I will just set up 5, let's say for U count. And let's do 25 for V count, like that. So technically, what I'm striving for is 5 boxes along the height and 25 boxes along the length. And then those segments that we have, I would just connect them to the domain input here. Bam. I end up getting the boxes, right? By the way, if it messes up, you know, not messes up, but if your 5 boxes are here in V and your 25 boxes are here, you know, so you end up with something like this, just switch the sliders around, right? And it's gonna work, right? So that is done. Okay, we have our twisted boxes. Back to our box morph, with our target box still waiting to kind of receive something. I straight up just plug in my twisted boxes to the box morph target input, like that. And that's it. I can now disable the previews of everything that I don't need to see. So I'm just kind of selecting everything, clicking the scroll wheel, and choosing the blindfolded guy here. And I end up with a bunch of really squished Schwarzschild surfaces. And they are squished because of the height of the boxes. So I can just change it. I'll change this to 1000. Bam. And I have my geometry here in place. Right? So now the nice part about this kind of approach. Well, the first thing is this is parametric, meaning that you can control amount of divisions, of course, quite easily. But you can also minimize Grasshopper, and you can kind of show selected and just show the surface in Rhino, right? And you can kind of mess around with that surface. So I can, for instance, rebuild it, and I can give it, sure, let's do 5 by 5 points, whatever, with degree of 3. Okay. So now this is this geometry has more points, so I can type in points on or hit F10, and I can mess around with the points of this geometry and see what happens, right? So these geometries that I've just made, or these Schwarzschild surfaces, will follow, of course, along my geometry, right, along my surface. So that's kind of neat. And we can bring this in, maybe force it to start breaking. Of course, if you push it too far, it's gonna start breaking apart. And notice how the connections here are messed up, and they are very similar to what we had with regular B-reps, with regular meshes and regular elements, right, before. So what I'm going to do is here under geometry, where it says open SubD with 24 faces, you know, the final output, I will try to join. No, it's not gonna work, huh? Okay, fine. I will not join the SubD geometry in Grasshopper. Rather, I will kind of talk a little bit more about it and about how it works and what you can do with it in Grasshopper. We will join it in Grasshopper in the end, but I still need to blab a little bit more about it. So let me find a place where we can really see it messing up. And I think, sure, this corner right here, I want this to be smooth, right? It's not smooth. I want it to be smooth. So I need to figure out how to make it smooth. Under surface tab, under SubD, you can see the components that Grasshopper has to enable you to work with SubD. So here you have a thing like subdiffuse and blah blah blah. Multipipe is also here, which is nice, but we don't care about those for now. A little bit of coffee. What we care about is control polygon, SubD control polygon. This thing right here. That's the flat geometry that we want. SubD control polygon will give us that flat geometry, right? And I'll hide this. Oh, wait, chat says, how did I make the things thicker earlier?
The little boxes.
Oh, that's the number slider here.
Oh, okay.
The height, right? If you don't have any height set, it's going to use 1 millimeter as a default for the for the thickness or the height of the boxes. But once you set it to, let's say, a mirror, they just become thicker. Anyway, coming back here, I just extracted the control polygon, the flat version of my SubD geometry in Grasshopper, and it extracts not as SubD but as meshes. And that's fine with us because it's going to be very easy to convert it back to SubD later on. So these meshes, I will join them up. I will use join. Or rather, let's not use join because, wait, I need to figure out how to explain this. So let's say we have an element here, right? Let's say this element is Bob, right? Bob is here. And this one is Timmy. Timmy is here, right? So we have Bob and Timmy connecting through this edge right here, right? So there are 1, 2, 3, 4 control points or vertices where Bob and Timmy are connecting. Meaning that if we just use mesh join, right, and we join these two guys up together into one mesh, those points where Bob and Timmy are meeting are still going to be duplicate points, right? They're not going to be merged into one point because join and merge is not the same thing, or join and weld is not the same thing. Meaning that the connection between Bob and Timmy will not smooth out, right? It's going to be read as a crease, but we want it to be smoothed out, meaning we need to join them, but also we need somehow to instruct Grasshopper that the duplicate points here need to be deleted. It should merge or it should weld the points together. There's like 50 different ways of how to do it. The one that I prefer is located in Kangaroo 2 as like a plugin for Grasshopper, and everyone has it. It's called Combine and Clean. If you write Combine, you will see it. Combine and Clean. Combine and clean a list of meshes, removing unused and duplicate vertices, right? That part, duplicate vertices, is the important one for us. Like that. Bam. So it basically takes a bunch of meshes, joins them up into one, and cleans up the duplicate points. meaning that once we convert this back into SubD, it's going to be smooth, right? The connection is going to be smooth. It's not going to be creased. And this is exactly what we're going to do now. We're going to take this mesh and we're going to convert it to SubD. So we go to our Surface tab, SubD subtab, and we find SubD from Mesh. This little guy right here, SubD from Mesh. We connect mesh to mesh like that. We can we can literally hide everything except the final output. And now we have a smoothed version, right? So all of these connections now, before they looked like this, like after the box morph, they looked like this, right? They were sharp. And now after we um, joined everything up and also like created the meshes from it, joined everything up, removed vertices and converted it back to SubD. Now everything is smooth, right? Neat and dandy. And of course you can bake it out and then enjoy it. So that is one thing that you can do with why are you like, oh yeah, tab. So that is one thing that you can do with it. That is pretty neat. And this is literally us pushing it a little bit too far, because you can see that the geometries here are messing up. It's too steep of a curve. If I look at it with EMAP, I can see that the smoothness of it is also, no, it is perfectly smooth. So there's absolutely no tell of connectivity issues or anything like that. Okay, so that is how you work with SubD. And before we finish up for lunch, or we have a kind of break, I'll show you one more thing. So those meshes that we have, right before we convert them back to SubD, we still have like a mesh here, and I'm hiding the SubD output, or rather, let me just delete it altogether and just look at the meshes, right? So these are just polygons, right? Everything that we are quite used to by now. We can really kind of mess around with this quite a bit, and let me reduce amount of like meshes in general. So instead of 25, I'll use 15, or maybe even 10, so that it's quite low resolution, right? So we have a bunch of polygons here, and we can work with these meshes like we normally would in Grasshopper, and we can do many crazy things with them. Question to the group: do you all have Weaverbird plugin installed? If you just go through the tabs in the top, does one of them say Weaverbird? WB. Waiting for anyone to say I can't find it.
I can't find it.
Me neither.
Okay, so you don't have it. That's fine. You can, by the way, just Google for Weaverbird for Grasshopper, and it's going to download an installer file for you, and it's gonna work. But if you don't have it, that's fine. We will figure out another way of how to do it. So let's say
Sorry,
every
Weaverbird.
Weaver, as in weave, bird, a bird that weaves. But we will be using it later on. So for now, don't worry about it. I will show you. Actually, I can show you this real quick, and then I'll show you how to manually do it. So Eurobird, the reason why I asked you if you have Eurobird is because it has this Eurobird's picture frame component where you can just give it any mesh, and it's going to automatically give you a frame around every polygon, right? So it's like an inset that is being kept. That's why I asked you if you guys have it. But if you don't, that's fine. We can still work without ViewBird. I'll go to the Mesh tab here in the top, and I'll find Face Boundaries component. Or you can just write Face Boundaries component. And basically here, once I connect my mesh output to the face boundaries input, it's going to and hide the face, hide the mesh. I only look at the newest one, the newest node. It gives me polygons, polylines, not polygons. It gives me polylines that are drawn around every face, right, of my shape. So these are basically closed rectangular polylines that I have here, right? A bunch of polyline curves, actually 1,200 of them. And I can take those curves and I can kind of mess around with them by, let's say, I can scale them, right? Yeah, I can scale them. So I'll use scale command on them. The geometry that I want to scale is my curves. The center point of scaling needs to be, for every curve or every polyline, it needs to be the center point of each polyline, right? So I need to get centers of all of the polylines. I can do that by just asking for, I think it's polygon center, right? Polygon center, yes. By asking for polygon center. And just connecting the boundaries to the polyline input here. And you can see that polygon center gives me 3 outputs. And those 3 outputs are basically 3 different ways of how you can calculate a center point of a shape, right? You can calculate it by its points, you can calculate it by the mean of its edges or average of its edges, and you can calculate it by its area centroid. In this case, we will be using the first output. I always use the first output. Center V for vertices. I just connect it like so. And you can see that every polyline gets scaled down towards its center point by a factor of 0.5. That's the default value. We don't want 0.5, we want to have control over it, so I'll just create a slider. Let's see, 0.7, connect it to the factor. And just kind of, once I move the slider, you can see how it, how these things change in size. So I'll keep it at 0.7. So it's 70% of its original size, right? And now we have our boundaries, right? Right here, and we have our polylines or scaled boundaries right here, right? We have a set of 2 curves. Okay, I will not be explaining data trees to you. So this part, you will just need to trust me, because if I started explaining data trees to you, we would need to expand this workshop by 1 more week, and we don't have that time. So this part is going to be super quick, but you will need to trust me. I will go to face boundaries on the boundaries output, and I will right click on it and choose to graft. What Graft will do is it will place every polyline in its own separate data branch. So every polyline will be treated separately, meaning that every scaled polyline is also going to be separated from the rest, which means that now when I use, let's say, merge on them, and I merge the boundaries with the scaled versions of the boundaries, I end up getting pairs, like two polylines for each data branch, meaning that, let's see, this boundary and its own scaled version are going to be secluded from all the rest. And it's the same thing for this boundary and its scaled version, and for this boundary and its scaled version. So everything gets kind of separated into pairs. The reason why I do that is because now I will be using a command loft to loft them together. And this is going to take a little bit of time because of course it's a really it's a lot of things to loft. But notice how it always lofts them now in pairs, right? But it doesn't kind of create a loft through all of them. If I didn't graft here, it would loft through all of them. It would just straight up crash, right? So grafting is very important. Keep that in mind. Okay, so we have our loft. Can you check, please, if you have a tool that's called Simple Mesh? Simple Mesh.
My computer is crashing, so I can't take Loft destroyed it. Sorry.
Yeah.
I have it.
Okay. And you didn't install any plugins, right?
No.
Okay, that's good. So that means all of you will have it. If your computer is crashing, just give it a little bit of time. Loft is going to be a heavy boy because we are using a lot of polygons, right? So there's a lot of surfaces that it needs to generate. It shouldn't crash though. It should kind of still generate them. Anyway, the way this will work now is all of our lofts are made out of 4 quads, right? 4 rectangular surfaces. I can kind of draw them out. You know, if we have one polygon here, we have another one here. So then that's one loft, or not one loft, but one patch, one surface. That's another surface. And that's the third one. And that's the fourth one, right? So 4 rectangular surfaces make out this ring of a loft. That's how it works. So simple mesh, as long as it's rectangular surfaces, it's going to take those lofts and it's going to convert them into meshes very, very easily, right? So it generates meshes from lofts. And if I hide this, you can, if I hide the lofts themselves, you can see how much faster it is, right? So there is a way also how to make it without the loft and how to make it fast, but I really, I don't want to expand this even further. So we will sacrifice the speed for convenience in this case. So we have simple meshes, right? I will now do one more thing that I will not explain, or rather I can explain this. So I kept talking about data tree, blah, 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 data tree branches and so on. Here I'm going to right click on the mesh output from the simple mesh and I'll choose flatten. What it will do is it will get rid of all of that nonsense, all of that data tree nonsense, and now all of the meshes belong, they're not in pairs, they're not in separate branches, they are in one big happy family, in one big list, and they are ready to be joined up. The reason why I flattened this is because if meshes weren't in one list, if they were in separate branches and I tried to join them up, it wouldn't work because they wouldn't see each other, so to say. In this case, I forced them to be in one list with flatten, and now they are ready to be joined up. And I'll join them by using the same command as I did before, combine and clean. Combine and clean, or combine and then find it. Yeah, there we go. There we go. So now we end up with one single mesh that doesn't have any duplicate points. And now I can do SubD from mesh on this. Disable that. Disable preview for that. And now I end up with something like this, right? Some sort of weird geometry that looks like this. Let me bake it out so that you can see better. Like that. Now it's getting a little bit heavy for me as well. But of course, since I kind of initially what I did was an inset, right, for all of these faces, right? So of course it kind of locks it down to more of a boxy look, but you know that's how it looks. Actually, I'm interested. Bridge. Can we bridge this? Hell yeah, we can. Never mind, it just broke. Cool. I'm running out of RAM. That's why. But so it does seem to work, right? And you can kind of use offset SubD to give it, let's say, 10 millimeters of thickness, and it's going to kind of thicken it up a bit, and it's going to look like that, and it's all cool and neat and so on. With EMAP, you can check for discontinuities, and it's going to take a little bit of time to generate, but it is going to eventually generate. Yeah, but we end up with something like this. So this is me generating complexity with Grasshopper, right? And showing you how to operate with this. So this whole part right here, phase boundaries, scaling them down, lofting them, creating a mesh, and joining up the meshes, is replaced by in ViewerBird is replaced by picture frame, by this element right here. And it's basically the story for any plugin that you install to Grasshopper. You can definitely do it with regular tools in Rhino or in Grasshopper, without any plugins. But plugins just make your life easier, right? And I will ask you to install a few plugins later on, but rather after lunch. But for now, we are kind of sticking to the raw Rhino. Any questions about this part?
Are we going to continue on this same script after lunch?
No. This script is kind of done because it's just to kind of show a concept. What matters is what you give it here, right, and what you give it here. Into SubD and into Surface. These two things matter the most. Everything else is just whatever. So this script is done. I'm going to honestly delete it. Don't need it. After lunch, we're going to jump into this. We will be doing this, and we will be using Kangaroo to kind of simulate it as well. Just like Antoni Gaudi did with his hanging chain models. So I hope you had a nice lunch. And during lunch, I just figured out that I will show you one additional kind of thing in terms of our approach with the bounding box and the box morphing. That same technique I've shown you, in our previous version. And this one is just going to be exactly the same procedure, but with another kind of mindset, another way of thinking about it. And I just wanted to kind of show it to you, to prove a point that it's much more necessary to understand how it works and the concept behind different Grasshopper scripts and how they work, rather than to know how to arrive from point A to point B with a Grasshopper script. So what I mean by that is, I'm trying to find words for it. So okay, so what I mean by that is I showed you all how to create a facade system, right? With that box morph tool. But that same tool, that same procedure, right? If you think about it, if you have a module, some sort of module, I've just created this form right here. If you have any kind of module, that module can be also be thought of as a part of a building, right? Just an architectural cluster. It doesn't need to be a facade element. It can be, you know, a room, a space, a floor slab, anything, right? So with that in mind, I can create a vertical surface, and I can, you know, use the same procedure and plug it in, and suddenly I can start working with it as if it's more of a tower rather than so it's some reason rotated. That's super weird, but as if it's more of a tower rather than whatchamacallit, a facade element, right? Or a facade. And for this to align, I will need to rotate it properly like that, and I need to figure out how to make sure that it all fits quite well, because right now it doesn't, as you can see here, right? It doesn't fit, meaning that this part and this part needs to be in the same position. I can kind of work around it quite easily, I think, if I just mirror this element to the other side like so, join them up. And this is not a tutorial, this is just a showcase of a concept of a, you know, set one SubD. It's just a showcase of the idea that I want to point across, that once you have a definition, you can a grasshopper definition, you can figure out many ways where to apply it, not just purposely for that particular application, for what it, you know, was initially intended for. Let me just do a quick custom preview, show it a little bit nicer. Bubblegum pink is always nice. Thing like that. Maybe less subdivisions. Maybe just 10. Like this. Maybe the bottom one. You know, I can rebuild this, of course. I can rebuild this 5 by 5. Actually, here I don't need 5. I can just do 3. I can rebuild this. I can turn on points for it. It's exactly the same things that we've done so far for, you know, in our tutorials, only that now I'm applying it to some sort of a vertical, you know, vertical weird structure thing. That, why is there a curve is there? Because I kind of extruded the curve to create the surface like that. And maybe this whole thing actually maybe this whole thing twists, right? I can just twist it, and it will twist. And here I kind of get these kinks that I want to fix. So I will just position it somewhere here, twist it like so, right? So we end up having these like I end up also sculpting with this tool, right? And then creating some sort of a spine tower thing, you know, a spine tower structure thing. And let's say at that point, I want to have more divisions vertically. I can just increase the V count, and then I have 2 spines rather than 1. So it's absolutely like this whole procedure is absolutely up to you, and you can achieve, you know, you can use this very simple script to achieve really complex results really fast. All you need is a surface, a guiding surface, and your element, you know, that the element that you use. And through the power of morphing and repetition, Grasshopper will generate pretty intense geometry. Just looking at it, cell SubD. Let's move it to the side. And let me join up all of these guys into one. Flip. Go. Just take a look at it. An map. Right? And I find this to be quite, quite beautiful. And it can be, even though it is twisting downwards, and these are not floor slabs by any means, but this can still become architecture. It can still kind of become structural sense. So that was something that I wanted to kind of use to get my point across. Sorry. Okay, but enough of this. Well, I'll maybe hide it. I might use this for the thumbnail. But another thing that I kind of teased you and will show you how to do it right now is those physics simulations and simulations of these kind of hanging chain models and minimal surfaces and whatnot, and basically any kind of physics-based simulation can be done in Grasshopper. The only question is, will your computer handle it or not, right? So the one that I'm going to show you is going to be pretty simple, and it's going to be basically a mimic of this, right? Of this roof right here, and yeah, I'll get right into it. So I will start by just kind of defining the floor plan, not the floor plan, sorry, but the area. Let's say the area of the building, of the rectangle, right? So I could draw a rectangle, or I can go to SubD tools and just draw a plane, create SubD plane right here. I can do either one of those. That's whichever you want. I will draw a plane. So create SubD plane. I'll create one. And here I can choose how many divisions I will have in X direction and Y direction. So in X direction, let's say along the length of my surface, I want to have 7 divisions. I don't know. I'm just figuring like any random number. 7 divisions seems fine. And along the Y direction, I want to have 3 divisions. Right? So 7 and 3. Then I'll start drawing from 0. I'll start drawing my plane from 0, and I'll give it length. Its length. So let's say, I don't know, 12 meters, 12,000 millimeters, something like that. And for the width, I will choose again like 5 meters, maybe 5 meters. Yeah, and I end up having this this plane right here, right? Nothing fancy, just a regular plane. All right, and the thought is that I will kind of create the form, the initial topology, the initial form of this, quite in a quite blocky way. I will create it already in Rhino, and then I will simulate it to higher precision later with Grasshopper. So I'm going to kind of have this, and maybe I'm just thinking, maybe we can take, let's see, this polygon and this polygon right here. Let's say these two are going to be our culprits, our columns, and I'll extrude those 2 polygons down, and let's just see what happens. Extrude SubD along the z-axis, so direction instead of free, I choose z. I'll just type in minus, let's say 3 meters, minus 3,000, and hit enter. This is what I get, right? And it's not, topologically speaking, it's not the same as what I want here, right? Because there shouldn't be any surface here and there shouldn't be any surface at the bottom. So I will simply just delete them, right? Delete that surface and the bottom one. Easy. Same thing on this side. That surface and the bottom one both get deleted. So now, topologically speaking, these two are exactly the same as this geometry right here. And you could stop here actually. I mean, you could really easily take this and start kind of pushing and pulling on the geometry until you will find, until it's going to just kind of start working for you, right? It will give you a decent result eventually. So you can do that without any problems. But if you want to be a little bit more precise, and I'm just really trying to scale these guys up, if you want to be a little bit more precise in creating, this kind of perfectly curving surface that is going to always be very, very strong in compression and, or rather, that will have forces that are always compression based within that surface, then you do need to do some simulations. And we will do that. So I guess let's start. This is where I would stop in terms of 3D modeling, and I would pick it up in Grasshopper and continue working on it, right? So in Grasshopper, I will actually just a second. I'm thinking if we should use Weaverbird. It's going to be quite convenient if we used Weaverbird. Maybe we should. Well, I do need to show you how to install Weaverbird either way, so let's do it. A little break in installing plugins. So you will need this plugin Weaverbird, and you can get it from the almighty internet if you just type in Weaverbird Grasshopper, right? And you just click on the first link that you see. You will find here, download Weaverbird for Rhino 6+7. Right? Once you download it, it will basically download this .gh file, right? So this .gh file will be downloaded, and you can open it up. You can just drag and drop it into your Grasshopper window, like that. And it's going to, for me, it opens up, but for you, it's going to say that, yo, you should download Weaverbird, right? Another like menu will pop up, which is going to basically ask you to download Weaverbird. So you just agree to it, right? You just say, yes, sure, download it, and it will download Weaverbird for you. And that's it. I don't remember if it's going to ask you to restart Rhino or not, but this is for you to tell me, right? If it is asking you to restart Rhino. I'll give you a minute or two. Yeah?
Seems to be working for me.
Oh, it just works.
Yep.
Okay, super. Well, that was easy, right? So what happened was that Grasshopper file had tools that were used only in Weaverbird, right? And Grasshopper recognized it, and it recognized that those tools belong to Weaverbird, and it automatically kind of downloaded it for you. That's very, very convenient compared to what we had to do in older versions of Rhino and V-Ray. One thing that will happen as well is once you have opened up that Weaverbird Grasshopper file, you drag and drop it in. your other file is going to be gone. Well, it's not really gone. You can find it still here, right below the X, for closing. Let me minimize that a little bit. Right below the X in your Grasshopper window, you can see the file name that you're currently working on. If you click on it, it will expand all of the loaded in files, right? So one is the Viewerbird one, and the other one is your file on which you work. I haven't saved mine, so mine is just called unnamed, right? If you click on it, you'll be transferred to your initial definition. These files, by the way, are called definitions, Grasshopper definitions. Actually, let's save this one. Well, I'll just show you how to save. I might as well. So I'll go to File, Save Document, well, duh. And we just kind of save it to anywhere we want. I'll just save it to desktop and call it AAHF Day 3. Whatever you want to name it. Yeah. Everyone's with me? I'll make it awkward. Someone tell me that you're with me.
I have a question.
Okay, go ahead.
I didn't get the tab for Weaverbird. I just got like the file just opened, but I don't have that tab.
Oh, that's strange. If you double click and you type in Catmull Clark, Catmull with double L dash Clark, do you see an option to get Weaverbird's Catmull Clark subdivision?
No.
Okay, restart Grasshopper, restart Grasshopper and Rhino. Save everything, close, open it up, and see if that's going. If you will have Weaverbird then. This goes for all of you. If you don't see Weaverbird tab, then you might need to restart for the menu. For these tools to actually load in to kind of show up. Hopefully they will. While you're doing that, I will be very slow in explaining, how we're going to continue working with this. So this thing right here that we have modeled out is not BREP, goddammit, it's a SubD geometry, right? So I am going to just reference it into Grasshopper, right, as SubD. That same hexagon thingy. Second, that same Grasshopper, that same black hexagon thingy, SubD node, right click on it, set one SubD, and just reference in your roof thingy. Have that done. And I always, when I reference something into Grasshopper, you always see this kind of duplicate geometry, right? One for Rhino and one for Grasshopper. I always then hide the one that is, in Rhino, so that I always work with Grasshopper then. We have that done. And now I want to convert it into a mesh. And the reason why I want to convert it into a mesh is because, simulations don't work, like physics-based simulations don't work with BREPs, don't work with polysurfaces, don't work with SubDs. They only work with meshes. So we're going to do that. I will, just like we did before, I will extract SubD. Oh, okay, it's not even extract, it's just called SubD control polygon. SubD control polygon, the low resolution one that we got last time. We use the same tool right now. So I hide the original SubD and I just look at the polygon and I can see, I can see it as a mesh here. Very low resolution. So we're now at this stage. question to the group. Once you restart Rhino, do you see ViewerBird tab?
Mine came up after I restarted.
It came up.
Yeah.
Okay, that's super, super. Because this is where we use it. So we have our mesh, right? And we want to subdivide it. By the way, this is going to be kind of a... I already explained it during day one, but I will repeat it now with all of you kind of having more information and understanding more about SubDs. So remember where I showed you how this low resolution mesh smooths out to become this curvilinear form? We can do that with subdivision here. So you can see that ViewerBird also has a SubD tab. That this ViewerBird SubD tab has nothing, absolutely nothing to do with Rhino's SubD geometry. It is subdivision of meshes into meshes with more polygons, right? So it has nothing to do with the SubD, but virtually or visually, they are going to become very, very similar. They will look very similar if we just take this low resolution mesh and we subdivide it. So we use SubD, ViewerBird's Catmull-Clark subdivision. Whoa, that's a big boy. Okay, so if we use that one with level, let's say 3, like that, right? And I will just, so that it's not in the way, I will bake it out just so that you can see better what I'm talking about. I bake it out and I move it here. So this is the mesh, right? Which was subdivided. And if I show, this is the SubD. Oh God, yeah, forgot that I can't do that. I need to copy it actually, like that. And this is the SubD. See how similar they are? And even if I do an EMAP on them, like the mesh seems super soft, as you know, just as soft as the SubD one, SubD geometry. That's because virtually what SubD does is it runs this algorithm of Catmull-Clark subdivision, only that this slider right here, we are using subdivision of 3, right? Level 3 subdivision. For our SubD geometry, it's going to be infinite, right? In infinity. That's the only difference. But yeah, you can get pretty close to SubD geometry with ViewerBird's Catmull-Clark subdivision as well. So that's an important note to kind of take or understand. But that was just, you know, visually for me to visually explain you how subdivision changes between level 0, level 0, level 1, 2, 3, and so on. I don't think it's gonna let me. Yeah, it's not letting me do level 4 because it knows that the more we subdivide, the higher the chance of it crashing. So we're not gonna do more than 3. Either way, we don't need this. I just wanted to show it to you so that you can see it visually. I'll delete it. Instead, we will use the original polygon. No, sorry, never mind. Control Z again. We will be using this, but we will not be using it at level 1, rather only at level 3. Rather, we will be using it only at level 1. So it basically will be subdivided from this to this, right? Every rectangular face will become 4 rectangular faces.
I have a question.
Yes, go ahead.
I do not see the rectangles.
Wait, I need to make it louder. Now ask the question.
I do not see the rectangles on the phone.
The what now? The edges?
Yeah, the edges, the rectangles.
Okay. You can enable if you go to display here in the top and you choose preview mesh edges, if you turn this on, then you will see them.
Yes. Okay.
Okay, so basically, the reason why I subdivide it only once and not 3 times is I don't want to deal with this amount of faces. No way. That's way too many faces. I want to find that sweet spot of having just enough resolution for the simulation to be kind of close enough, and also yeah, so having just enough resolution for the simulation to be close enough, to the real thing, to the ideal geometry, but also not having too much resolution so that once I get the geometry out of the simulation, I can't really do anything to it because it's just, a mess. So many polygons are there. So I'm using subdivision level 1. One last thing that I want to fix is these naked edges, right? And smoothing of them. You can see that when I'm not subdividing, I have this sharp edge here, sharp corner here, sharp corners here. Maybe I want to keep them, huh? Maybe, just maybe I want to keep them. So I'm going to, or maybe I don't want to keep them. Do I want to keep them? Sorry, I'm thinking to myself. Actually, I do like it when it's a little bit smoother. God damn it. Well, just to be pedagogical about it, if you want to make it sharp again, if you don't want to round off the corners as you're subdividing them, you can go to smooth naked edges, this input here, and you can plug in toggle, Boolean toggle, and you can plug in false into it, right? So it's going to keep the corners sharp. Or you can double click on the false, the word false, and it's going to change to true, and now it's going to smooth out, right? So you can switch between them. Honestly, I prefer it to be smooth, so I'm going to keep it, I'm going to keep it smooth wherever. I think that looks better. Okay, so we have that. We have our mesh that is slightly subdivided, slightly smoothed out, and is ready to be simulated. So for simulation, we will be using Kangaroo. And I assume all of you have Kangaroo plugin already installed because it ships together with Rhino these days. Wait, that's not it. That's it, right? So Kangaroo. If you don't have it, speak now.
We have it. Kangaroo number 2.
Yes, exactly. Perfect. Okay, so Kangaroo, I always show this tutorial, so I might be a little bit too fast in terms of explaining things, but just stop me if something doesn't make sense. But Kangaroo is a physics-based solver, a physics-based simulation engine, which moves points around. Points of a mesh or just points, doesn't matter. In this case, we will be moving the points of a mesh around, according to some sort of a physics rules that we will set. So with Kangaroo is actually the only plugin that I use backwards, meaning that I don't work from left to right, but rather with Kangaroo, I work from right to left. And this will make sense in just a second. Under Kangaroo plugin, under subtab main, you will see a node that's called solver. That's the brain, right? That's the main thing in Kangaroo. That's the thing that does the calculations. So let's grab it and let's put it in our definition, right? Solver. So this thing calculates, right? Solver, for it to work, it needs at least 3 inputs. It needs a button to turn it on or off, right? So for that, I will use a toggle, Boolean toggle, like that. And since Boolean toggle is right now set to false, the solver is not thinking, right? It's off. Once I double click on the toggle and turn it to true, it's going to start thinking, right? But right now it has nothing to think about, so it's kind of, not doing anything really. So I'll turn it to false again. Then tolerance and threshold, we don't care about those two. Don't worry about them. These are advanced later. Later, if you are, if you learn more, you will kind of, you'll get to these. Reset button is a button. Already said it. It's a button, right? So we create a button and we plug it to reset. So think of it this way. You want to simulate how a ball hits the ground, right? You have a ball, you have a ground, you kind of plug things into the solver, it calculates and it shows you an animation. Ball just hits the ground. And what if you want to do it again, right? What if you want to simulate it again? Well, that's where the reset button comes in. You just click the reset button and it kind of redoes the calculation and the simulation for you, right? While on or off is just, is it working or is it not working switch. And then, so that's the reset button. And then we have the main thing, goals. What is it going to simulate? What kind of instructions are we giving to the brain, to Kangaroo? So for goals, we will have multiple goals. We will have multiple inputs. And I will be using what's called a merge tool. Honestly, when you hover your mouse over the names of the tools, it gives you a pretty good explanation usually of what those tools do. So in this case, merge is merging a bunch of data streams. Data streams are basically just a bunch of nodes or a bunch of tools are being merged into one. If you have a bunch of curves on one hand and you have a bunch of points on the other hand, you can use merge to have one list of a bunch of curves and a bunch of points. If that makes any sense. So that's merge. And we'll connect the result of merge to the goal object, like that. And basically, stuff that will go into data 1, data 2, and later data 3, data 4, data 5 of merge is going to be our goals, which we need to figure out. And to figure out our goals, we need to know what we want to achieve, what we want to simulate, what we want to do. What do we want to do? Well, we want this surface right here to have the least amount of surface area possible, right? With given boundary. That with given boundary is a very, very important thing to note, because if we just say, this surface needs to have the least possible area, just make it have least area, least amount of area, let's say it like that. Then what Kangaroo will do is it will just contract the whole surface into a single point, and it will say, yay, 0, the area is 0 now, but we don't want that. We want this to work as if it's a membrane. And actually I can show you what I mean exactly. Fry Auto, if you don't know him, start Googling immediately. Very smart guy. Won Pritzker Prize for his tents mostly. And he's famous for doing these soap bubble experiments, which so he used soap bubbles to find geometry, and to find geometry, and to figure out how these huge, large tents will behave under tension, right? So these are tension-only based structures. It's basically, you flip it around and it's compression-only based structure again. But basically he used soap bubbles. We won't use soap bubbles, instead we use kangaroo, right? But the experiment that we want to do is something similar to this, right? We want to tension it, to create tension inside of the structure and find the minimal surface. For that, what we need to lock the points around the perimeter and also around the, the edge of the column in place. Those points shouldn't move. They should be static, or else everything is going to collapse into a single point, right? And then we need to say that the mesh, that is locked on its perimeter inside the mesh needs to try and contract as much as possible, like a stocking material, right? Yeah, and that's basically it. We could add gravity to it as well, but I think gravity is not going to be necessary for this particular example. It's just the tension forces are going to be too strong for gravity to have any effect whatsoever. So we're gonna do that. Incidentally, the first goal that we're going to give it is going to be called show. Show with a light bulb. Show. And that's going to be goal number 1. And it's going to be basically what show will do is any geometry that we plug in to show will be pushed out from the solver once it's done the calculations, right? So this is basically what kind of geometry are we working on, right? And we are working on our mesh, right? So I just plug it into show. Oof. So we are done with goal number 1. Honestly, this is enough for the simulation to work, and I can kind of explain what happens now with this. If I turn on the simulation right now, what happened in like 1 millisecond was that the solver checked what kind of goals it has, and it found only one goal that says, show this geometry, show this geometry. And the solver just went, yeah, sure, here you have it. And the output is the mesh, right? So it just kind of shows us the same mesh without changing anything. And since it's done with the goals, it just goes like, yeah, done, and stops. So the simulation here is very short and very boring, but it is working. So we're happy with it. And I will turn it off. And honestly, I'll hit reset just in case. Hit the reset button just in case. Okay, so that's our first goal, a very boring one. The second goal is going to be a little bit more interesting, and it's going to be contract, right? We want it's not going to be called contract, but we want the mesh to shrink, to try and shrink, right? So we, under Kangaroo 2, under goals mesh, we will find a goal that is called edge lengths. Edge lengths. Right? So this one. And I'll put it here. So that edge lengths goal is going to be our second goal, and we've connected to data 2. The solver should be freaking out, but it's not. I wonder why. Very weird. Anyway, it's not freaking out, so I guess that's fine. But edge lengths is basically what drives the mesh to contract, because this goal will take every edge of this mesh and will give it a new length factor, right? Factor is the key word in this, and it's basically proportion, right? Factor 1 is the original length, factor 0 is 0 length, factor 0.5 is half of the original length, right? So it's basically like you multiply the existing length, the current length, by the factor, by the number. So here the length factor should be 0 because we want it to contract to, try, and this mesh should try and contract to nothingness, to 0. Also which mesh? Well, this mesh. like so. And the strength of this goal, I have no idea, so I keep it as 1. This is how strong the forces are. It's like an internal number, so we don't really care at this stage. I will just keep it as 1. Right. So what this will give us, I will minimize everything. Sorry, I will disable preview of everything except the final solver. I will click reset and I'll turn it on. And you can see that it just simply shrinks to 1 point. And it's happy about it, right? It says converged, meaning I found a solution. And the solution is now all of the edges are 0 length, meaning the mesh area is also 0 length. If I click on reset, you can kind of see it really quickly contracting every time I click reset. The reason why it's doing that is because there's nothing holding it from contracting to 0. Same thing would happen with a soap bubble, right? If you didn't have that frame that's holding it in place, it would just kind of pop, right? It would just kind of contract to 0. Well, in case of a soap bubble, it might produce an actual bubble, but that is a super unstable system. I don't think it would. But there is a possibility that it would do so. Anyway, with Kangaroo, it will never do that. It will always contract to a single point if nothing's holding it. This is where third input comes in, third goal. The third goal is going to be get the perimeter of this mesh. All of the points that are on the perimeter. Get all of those points and lock them in place. Don't let them move. So locking points in place is done by anchor, by a tool that's called anchor. And that connects to D3, to the third input right here. And it asks us for 3 inputs. We care only about one of them. Target, we will not be changing the target. And strength, the strength is set to be 10,000 compared to the strength of this, of the edge lengths being set to 1, meaning that the anchors are much, much stronger than the edge lengths, which we want. We don't want those perimeter points to move at all. So the only thing that we need is the point, or points that we want to anchor, right? The perimeter points. And thankfully, Kangaroo has this really neat little tool that I can't find. Can you check if you have naked vertices component? Naked vertices.
Yes.
Yes? Okay, good. Where is it though? I just want to find it. There it is. Okay, so it's under Kangaroo 2 mesh naked vertices. So let me explain what naked vertices means. And I can do that by showing you the original mesh. So let's say this point right here, right? This vertice right here is surrounded by 4 polygons, completely surrounded by 4 polygons, meaning that is a clothed point, right? A clothed vertice. While this vertice right here, this point right here on the edge, is only surrounded by 2 polygons, and on the other side, it's open to the environment, let's say it like that. Or it's on the outer edge, right? Meaning that it's a naked vertice. That's all it means. So if I connect the mesh to my naked vertices input right here, I will get both closed points, closed points and naked points. So I just choose to use only the naked ones, and I connect them as my anchors, and that's it. Now I can disable the preview of everything here, and I can do some resetting and click on I double click on the Boolean toggle, and you can see how my mesh immediately finds a new resting position. Does it work for you? If anyone's following.
Not for me.
Doesn't
Not
work.
for me. It says on the edge length.
Mm-hmm.
It says it fails to collect data from the mesh.
From the mesh. Have you connected the mesh to it?
No, sorry.
Okay. That might be the the culprit. What about now? Does it work
Yeah,
now?
sorry.
Super. Good. Happens. Trust me, happens to all of us. Okay.
Now it works.
Okay, great. So now we have a working like a working simulation, right? That will always kind of lock a perimeter of a mesh in place, and it will find a resting position. So for a minimal surface, it will make a minimal surface out of that perimeter. So I can kind of to just make my point, you can see that the SubD geometry and my minimal surface are very different, right? It found that this band right here makes it so that first of all, the forces will transfer from one column to the other much easier. The second one is that it requires much less surface area to do it that way rather than having it flat. But if I, for instance, let's do something like this. Bam. See how it immediately recalculates? It immediately kind of changes the the positioning. The points are freaking out like crazy, but if I click on reset, it kind of resets properly. So it will constantly find the resting position for any kind of form that you give it. Okay, so we have that working. That's good. That means we can move on with this definition. So the output from the solver is always basically all of the crap that came in here. But since we used show as our first input, that means our first output from this list, I will just quickly show it to you with panel, you don't need to follow. The first output of this list is going to be the mesh. And everything else is just, actually I need to, sorry, you do need to do this though. The O output, I will right click on it and choose to flatten, just to get rid of this separation between the mesh and everything else. It seems like we want it, but we really don't. So I will just flatten the O output. And now everything is in one list. And I know for a fact, again, since show comes in first as the first goal, the mesh is always going to be first, right? And all of these points and lines are going to be later. So I just always need to to continue working on this mesh, I just always need to extract it first. And I can do that. I can do that by using list item. List item. Like that. Connecting it. And list item by default, even without any other additional input, you not giving it index or wrapping information, it will give you the first item on the list, which incidentally is the mesh. It's as if I've planned for it. Okay, so we have it here. We have the mesh here. And from here on out, it's exactly the same procedure as what we've done with God damn it, I can do it with the previous tutorial, right? We take this mesh, we convert it to SubD. I don't remember. Wait, let's go to surface, SubD, mesh to SubD. or no, sorry, mesh from SubD. SubD from mesh. Yeah, that's the tool. We connect it. And we can bake out the SubD geometry. I assume you all are familiar now with baking stuff. So you just right click on the output that you want to bake and you choose the egg icon. And then you choose which layer and hit OK, and it's going to bake out the SubD geometry for you. So we end up with this beautiful geometry that is, you can see that this curvature right here, let me show you the original one selected. Let me make a copy of the original one and hide it now. So on the left hand side, we have the relaxed one, the subdivided and relaxed one, right? And on the right hand side, we have the original one. So see how the original one has these kind of polygons where there is high tension, while the relaxed one, you know, doesn't have it. This just kind of proves the point of it working properly. Of it being kind of smooth, continuous surface, a much more continuous surface. And now, honestly, you could solve it in Grasshopper, but I will be solving it in Rhino. How do we make, you know, the columns proper and not like this? And it's as easy as just taking the control points, moving them vertically down, you know, to the correct height, and just messing around with the, you know, move vertical, messing around with the control points until you find, let's do it this way, until you say that, you know, this is the form that I want. Intersection, turn that one on, bam. So don't be afraid of using helper lines as well. I really often use helper lines like that, you know, when I need to kind of bring in my my geometry to the corner, let's say. So that,
sorry, can I?
yeah, go ahead.
I can't seem to bake my my geometry.
Oh,
it says
really?
another command. It says another command is
Oh
running.
yeah, go to Rhino and hit escape. if some command is running in Rhino, it will not let you bake.
Okay, thanks again. Sorry.
I honestly, it, like, to figure that one out, it took me like a year. I thought that something's off with my Rhino and that, you know, it's a broken piece of shit program. Apparently, nope. There's always a problem with someone in between, you know, the screen and the chair. Usually that's the case.
I got another question,
Yep.
just to see if I got this right. Could you describe this like a blanket connected only in the edges and then it like falls down?
More like a, no, more like a nylon stocking.
Okay.
Much closer to a nylon stocking, being connected to the edges and being, and then let's say this edge, this portion right here being stretched out, and you know that the whole stocking kind of stretches to fill in that arc, much closer to that than a blanket. A blanket wouldn't have, I can show you actually. So let's say we have, and this is not, you know, not a part of it, so it's going to look super stupid, but let me show you just the mesh. And for this, actually, we will want to have, I'll delete the SubD part, and I will show it with level 2 subdivision because we will want to have more resolution for this example. Oh, it's gonna be so stupid. Let me reset real quick. I'll turn off the solver for a bit. So blanket doesn't try to contract really, right? It's all of the strings in a blanket try to keep their initial length, right? So they crumple. If when you fold the blanket, it crumples. So length factor is actually 1. But then for a blanket, for it to fall down, we need gravity. And this is not, you don't need to follow along. This is just kind of a showcase, I guess, of the tool. So there's no need to follow along here. So for gravity, I would probably go to mesh, and I would say that there is certain load on every vertex, right? Like every point receives some sort of a pushing down force. So vertex loads are being applied to this mesh, and the strength of them is I don't know, like 100, maybe something like that. I have no idea how if that's a lot. And now let's see how it's gonna work. Okay, shit, that's upside down. So it needs to be negative 100. Negative 100. Right? So it kind of just falls down. So that's more like a wet blanket, right? It just kind of being like this, and then as I increase the gravity, it just kind of bulging down and falling, like stretching down. So that's the blanket part. And also it's not really accurate because blanket has self intersections and crap like that, and it's a whole different thing. I actually worked, this is something that I find interesting, and I worked on it quite a bit. I'm just going to try and find it real quick on my channel. Oh, you need to do that like that. Scroll up. I really don't. I need to clean this up. So many. Yeah, there we go. Stuff here. Stuff that is here. Parametric loft simulation. So this dress right here was simulated with. So that dress right there was simulated with Grasshopper, with Kangaroo, from cut patterns, right? So you draw out the cut pattern for the dress, and I also drew out these kind of bunny rabbit ears, and it kind of shrinks to the body, and you turn on the there's a bunch of collisions and so on, and it kind of falls down, and then you simulate the lady, or you animate the lady, and it should be somewhere here. Yeah, now it works like a, like a rug or like a cloth, and this takes so long to actually do. I'm trying to find yeah, that's me trying to fix the freaking shoulder, because the dress just slid off from the shoulder, and it took me like half an hour, to fix that part, or to simulate that part rather. But basically by the end of it, you do get, a pretty convincing dress. Yeah, that's a long way of me saying that no, this is not like a like a cloth simulation. It's more like a soap bubble simulation type of thing.
That's very good. Thank you.
Yep. Right. So we have this going. I don't really need the kangaroo part anymore, or the grasshopper in general anymore. I can show everything that's remaining in Rhino, so I just minimized. Grasshopper. Right, so from here on out, it's just basically cleaning up stuff, making sure that all the corners are in the right places. So for instance, this guy is not, and I kind of want it to be, so I'll just draw a few polylines here and there, and just push that corner. Bam, right here, perfect. Tab, looks pretty. Honestly, I don't like this edge right here. I would probably switch it, or maybe it's possible to just delete this. You know, this is where you start messing around with it. And you say, well, screw it. I don't really want, I'm using slide for this, by the way. You just say, I don't really want it to be a perfect, you know, compression-based geometry. I want to mess around with it. And maybe it has some sort of a window into the courtyard. You know, it will have a window into the courtyard in this place. In our design here, we kind of had a similar approach, but instead of cutting out parts from the polygons, we just used Boolean difference, right? Just made like where you can see them. Kind of can see it there, but not really. God damn it. No renders of it, but yeah, you can see it here. Just use Boolean difference to cut it out. Yeah, but that's basically it. Then you just do SubD offset, or probably offset SubD, right? Yep, I always mix those up. Give it like a reasonable amount of thickness, something like 250 mil. And yeah, that's that. Questions? I would definitely take all of these bottom surfaces here. Think of questions while I'm doing this, because the tutorials are done now. So it's time for you to use me as a resource. I just flattened everything out
This
here.
basically makes it more. Sorry. This basically makes the structure more buildable. Can you say that? It's more reasonable way to build.
It's more rational. That's for
rational,
sure.
yeah.
Yeah, that it is more rational. That's for sure. Is it more buildable? Well, everything is buildable. Will this make it more expensive? I guess that's the main question. Yeah. Yeah. I mean, is this, you know, more expensive? Is this kind of structure more expensive than second shell thickness 250? Then this kind of structure? Hell yeah, this is more expensive. Multiple times. So if buildability is kind of calculated through economical means or through expense, then this is more buildable. If we're talking about everything else, then I would say that this this makes more sense from multiple other perspectives. This is a stronger structure, first of all. This is, you know, if you were to put a crap ton of snow, you know, tons of snow on top of this, and you were to put the same amount of snow on top of this structure would break faster than this, right? Because this is the forces will transfer much more evenly, while here this center line will give really quickly. Well, relatively quickly. Yeah, and also roof that becomes a column, that becomes a wall, an interior wall. I find something pleasing with that. I don't know. you know, where we don't distinguish between what's a roof, what's a wall, and what's a column. You know, when you stand here, you kind of start say, you could say that, well, this is a wall and this is the ceiling, but you know, in reality, it's just a column that's you know, kind of going down. Just I don't know, I kind of like it. What else? You can log the perimeters in place and you can make it even more sharp if you want to, right? Because here I have like this filleting. You can kind of sharpen out the fillet by introducing crease to the bottom perimeter, bottom perimeter, but I don't think that's necessary. Let's see, crease, tab, ew. Oh, right. That's if this happens, by the way, you know, if it's making if it's creating a spiky boy, just make sure that you're not creasing these edges, right? The in between edges are not creased. Only the perimeter. Remove crease. Right. Then it's soft. Soft only in one direction and hard in the other. Also, there's also always bevel. I'm sorry. Wait, wait. No, please stop. No. Crease. Yeah, good. There's always bevel to make it sharper. More questions?
Could you like if you assume that the wind loads will be heavy on the building, could you change the direction of the force, or would that be very
Oh yeah, absolutely.
hard?
No, absolutely. So you want to simulate how will the building. Wait, what do you want to do? The first question is, what do you want to do?
If I like in Kivik, there's probably a lot of wind from the sea.
Yep.
And I want to optimize the building for that as well.
But then so you don't simulate, because if you simulate wind, I can show you. You know, we have this, right, this structure, and let me actually length factor 0, right? We want it to contract. So we have this kind of original structure like that. And you want to say, okay, the wind is blowing like that, or from that direction, that there is wind blowing. So you don't optimize it with kangaroo. You can simulate with kangaroo wind actually blowing from that side and this acting like a piece of cloth. And you can do that if you go to goals point. You can apply load for every point. Let's say for clothed ones. Remember, naked points, clothed points. Clothed points are the interior ones. You can apply the like a force to every interior point by just giving it a vector. So let's say our vector is in y direction. It doesn't need to be x, y, or z, but this is just for me to be faster about it. In y direction, and let's say its strength is 100, you know, stupid strong vector. And we just connect it to, you know, as one of our goals, and I press reset and press play. You now can see that, you know, the whole structure is being pushed to the left. If I turn this off or decrease it, the structure is now normal. So this is just basically adding additional force that is pushing it. By no means is it, used for optimization.